Hello, I'm Mehrnoush Raufi from the University of Pittsburgh. In this video, I'll be presenting our paper IR-ORAM, Path Access Type-Based Memory Intensity Reduction for Path-ORAM. With the wide adoption of cloud computing, the privacy is a major concern. Consider this scenario. User accessing the cloud server which provides a secure processing. So as a user, we trust the CPU, but not the memory bus nor the memory modules. Therefore, an adversary can snoop on them. Users may store their data encrypted, so the data itself is safe, but the address is transmitted in plain text in commodity DRAM. So the memory access pattern can leak information to the adversary. The question is how to protect the access pattern. Recent studies tell us to use oblivious RAM, ORAM for short. What is ORAM? ORAM is a crypto primitive to obfuscate memory access pattern. ORAM controller locates in the memory controller. ORAM organizes the memory blocks in a tree structure in the memory DIMMs. ORAM tree maintains the data encrypted and permutated across the memory. The idea is when a user program requests a block, the ORAM controller translates it to many block accesses so that no outsider can tell what block the user program is actually accessing. Note that ORAM controller is within the trusted base and everything else is untrusted. Now let us take a closer look at the Path-ORAM, which is a popular ORAM protocol. First of all, it organizes the memory blocks in a full binary tree. If the tree has L levels, then it will have 2 to the power of L-1 passes from the root to the leaves. Each node is a bucket that has Z slots. A slot can hold real or dummy block. Real blocks are actually the user data. Each real block is randomly mapped to a path after each time it is accessed. And the mapping is only known by the CPU in the trusted base. 50% of tree is always filled by dummy blocks to ensure the protocol doesn't fail. Because the mapping process is random and ORAM needs to make sure there's always enough room on any path a block is mapped to. Let's see how the block access works in Path-ORAM through an example. Consider a tree with 3 levels and 4 slots per bucket. We want to access block A. First step is to look up the position map in the CPU side to see which path the block A is mapped to. Here it says path 0. So next we initiate a read path operation. All of the real blocks on path 0 are brought into the stash. Then they're decrypted, and there it is, that block A. Since block A is accessed by the CPU, it has to be remapped to another path. So we remap it and update its path ID. We also update its mapping in the position map. At last, it's time for the write path operation to write everything back to the tree. Starting from the leaf, considering this bucket, only blocks with path ID 0 can go here, like block F and C. Next bucket can both accommodate blocks with path ID 0 and 1, since both path 0 and path 1 cross this node. There's only one candidate here, and it's block E. The bucket at the root can accommodate blocks with any path ID since all passes cross here. And the new path ID of block A is 2, so it can only go here. Blocks are re-encrypted and written back to the path. In a real scale, for example, to protect the 4 GB user data, the ORAM tree requires 25 levels with 4 slots per bucket. Given that the top 10 levels are cached on chip, the path length would be 16. This means one user block request is translated to a read path operation, which is 60 reading blocks, followed by a write path operation that is writing of 60 blocks. So path access consists of many memory accesses, and it is very expensive. We refer to this as the first memory intensity factor of Path-ORAM. Later on, we explain how IR-ORAM reduces this intensity. Continuing on memory intensity, there are multiple path types, assuming we want to access block A. First, we need to know its path ID, so we look up the position map. But in the real scale, position map itself is too big to fit on chip. So as prior work suggests, the position map is also stored at the ORAM tree. And then the position map of the position map is stored on chip. However, if it doesn't fit on chip, the recursive hierarchy goes on and on until it does. Prior work suggests to keep a position map look-aside buffer, or PLB, to cache the postmap blocks. So in a case that there is a PLB miss, a postmap path access is required to retrieve path ID of block A. It may take more than one path access to retrieve the postmap block for block A. Once the path ID of block A is known, we can access a path to get the block A itself, and that is called data path access. There is also another path type called dummy path accesses. It actually happens when there is no request from the user. But in order to provide the timing channel protection, the path accesses have to be made at a fixed frequency like this. So there will be times that there's no pending user request. In that case, a random path is accessed where no block is remapped. Note that all of these path types are indistinguishable for an adversary because all passes have the same length. If we look at the breakdown of path access types in Path-ORAM, we realize that aside from the data path accesses, postmap and dummy path accesses also account for a significant portion, 33% and 11%. So the second memory intensity factor of Path-ORAM is that there are different path access types other than data access that contribute to this intensity. Later on, we show to tackle this problem, IR-ORAM reduces the number of each path type. We made a key observation about the tree utilization trend. We ran an experiment with 4 billion path accesses. Then we took a snapshot of average utilization across levels. A utilization rate of 0.5 means on average bucket of that level are full or half full with real blocks. We observed that top levels have high fluctuation, middle levels have low utilization, whereas bottom levels are highly utilized. If we project the ORAM tree on this figure, it will be like this. This is the capacity distribution. The 5 bottom levels account for the majority of the capacity, so the high utilization is expected. In contrast, middle levels are utilized no more than 1/3, and they account for only 6% of the capacity. Yet, each level contributes the same number of blocks to the path length, and we exploited this phenomenon and came up with IR-Alloc, a utilization-aware node size allocator. It keeps the top and bottom levels intact, but reduces the Z parameter for middle levels to 2 and 3. By shrinking the middle levels, path length is reduced significantly with a negligible impact on the capacity. Considering this configuration for level 10 to 16, Z2, and for level 17 to level 19, Z3, the path length is reduced from 60 to 43. Revisiting the first memory intensity factor, IR-ORAM reduces the intensity of each path access by reducing the path length. Note that still different path types are indistinguishable because they have still the same path length. Here's another key observation. It's regarding the heat across the 3 levels. The figure shows what percentage of requested blocks are found in the 3 regions. The top 10 levels account for less than 100%, yet they receive 23% hit. Here is why. A block sinks down the ORAM tree gradually. Open a map, the block is first moved to the top levels, and later on it is moved to the deeper levels. And meanwhile, due to the program locality, top region sees a relatively high hit rate despite its small space. Considering an example, if block A resides on the top levels of the path, in the case that its position map is already available, then no memory access will be required because the top levels are cached. However, in the case of PLB missed, a postmap access is required, which is unnecessary, given that the requested block is going to be found in the treetop cache. This can be actually mitigated by redesigning the stash, which brings us to our scheme IR stash, a double index stash implementation. It contains a fully associative stash as the regular stash, and in addition, it has a set associative stash to cache the treetop. This stash is accessible also by Path ID with the help of the little table that maintains the tree structure. In this way, if a block is a hit in treetop cache, it will be accessible via S-stash lookup. So no postmap access will be required. Note that F-stash cannot be extended to cache the treetop because such a fully associative cache would need an area larger than LLC. That's why we proposed S-stash. IR-stash reduces the postmap accesses by 51%. Regarding the inevitable dummy accesses for timing channel protection, we propose IR-DWB. It converts dummy path accesses to useful early writebacks. It keeps track of soon-to-be LLC victim for eviction and tries to make them clean by piggybacking on dummy accesses. It converts the half of dummy path accesses into useful writebacks. Revisiting the second factor of memory intensity, IR-ORAM reduces the number of postmap accesses and converts dummy accesses to useful data access. For the evaluation, we use a trace-based simulation. We collected traces using pin tool on a spec and parsec benchmarks. The table shows the system configuration. We used a 4-issue wide out-of-order processor with 4 memory channels and 2 megabyte LLC. We protect 4 gigabytes of user data in an 8 gigabyte ORAM tree with 25 levels and 4 slots per bucket. Blocks are 60-byte cache lines, and the stash has 200 entries, and we cache the treetop 10 levels. We have 64 kilobytes PLB and 512 kilobytes on chip position map. And here are the performance results. IR-Alloc improves the baseline by 41%, IR-stash by 27%, and IR-DWB by 5%. And altogether, IR-ORAM improves the baseline by 57%. To summarize, Path-ORAM is an expensive crypto primitive to obfuscate memory access pattern to preserve the user's privacy. It's very memory intensive though. Firstly, path access consists of many memory accesses and is very expensive. To overcome this, IR-ORAM reduces intensity of each path access by reducing the path lengths. And secondly, there are different path access types contributing to the memory intensity of Path-ORAM other than the data path access. Therefore, IR-ORAM reduces postmap accesses and converts dummy accesses to useful data access to reduce the intensity of Path-ORAM. Ultimately, IR-ORAM improves the performance of the baseline by 57%. Thank you.